Hi, my name is Abdulrahman Alobaid, and I'm working with my teams. Uh, his name is Casey, and the other one, his name is Sunil. So we're gonna work about the project too. Uh, and this. Oh, so in this problem, we are giving a system with two bundle with masses M1 and M2 on them, both hanging from strings of line, which is L. Ball one starting from rest at some known height and falls calls with balls two, and we want to find final heights for each ball rises to after collision. So our estimation are that there is no significant drag force on either ball, so energy will be conserved as the mass is moved through the air. Also, the ropes are ideal ropes, so there is no energy transfer onto the ropes. Again, conserving energy of the two ball system. The collision is defined as elastic in the problem statement, so we know kinetic energy will be conserved in the collision itself. Finally, since the collision will happen over a very short time interval, we will assume it's small enough to exclude any significant external force on the two-ball system during the collision. So momentum is conserved in the collision. Now here's the basic setup of the system initially, where we find the initial height in terms of L, the length of the string. Here, considering the three separate phases of this motion as one, the fall of ball one, two it will be the collision, and the three it will be the raise of the balls post collision. We have energy diagram as shown here. In phase one, the system included the ball and earth as gravitational positional energy of the earth is transferred to kinetic energy of ball one. Next, in the collision, ball one will transfer some amount of kinetic energy to ball two, such that their final total equals the amount ball one has initially. Finally, in phase three, each ball transfers its kinetic energy back to position energy of the earth as it raises to its final height that we are solving for. For the collision phase, the momentum will be conserved, but the direction of each ball's final momentum after the collision will depend on their relative masses, as explained later. We do know the final momentum of the two balls together as a system must equal the momentum of ball one just before the collision.
Uh, our process to analyze this motion was to first consider how ball one's initial height and mass would determine its kinetic energy, and thereby its velocity just before the collision when it has no more potential and all of its energy has transformed to kinetic energy. To do this, we equated the initial potential energy, mgh, to the kinetic energy just before impact, 1/2 mv squared, and we solved for that velocity. This velocity is the final velocity of the falling phase of the motion, but that is also the initial velocity heading into the collision. And so we use this velocity to determine the initial momentum pre-collision, and then we set that initial momentum equal to the total momentum for both balls post-collision. And so setting those two momentums equal to each other, I guess three separate momentum expressions, we solved for the V2 final, and we got this expression for V2 final. Then we used that velocity for ball 1 before the collision and set up a new equation showing the that's what we did. We set up an equation to solve for final velocity based on the conservation of momentum. Okay, next, after looking at momentum, we looked at the conservation of energy during the collision. Since it's an elastic collision, we know that the kinetic energy before and after, the kinetic energy of the total system before and after collision have to equal. And so we set those equal to each other. We plugged in the value for initial kinetic energy we had just solved for, mgh, from the potential initially. And so now we have an equation with two unknowns here, V1 final and V2 final. And this is actually our second equation with these two unknowns. So we have two equations, two unknowns, and that is a solvable system of equations. So to solve that system, we put these two separate equations together. We simplified that into a standard quadratic form, ax squared plus bx plus c equals 0. And that was a pretty gnarly equation, so we plugged in the expressions for a, b, and c into a program on the computer to solve it, Symbolab, and plugging these values in for a, b, and c, we get these two roots boxed in here. The first root we see is a general solution to the final velocity for ball 1 for any two given masses, m1 and m2. The second solution, the negative root 2gh, is basically what you would get if the second mass had zero mass, where the ball swings up to its initial height that it started from. Okay, finally, we plugged our result for the final velocity 1 back into our original equation for final velocity 2, and we simplified to find final velocity 2. However, what we're actually looking for in this problem is the final heights, so we had one last step, plugging these two final velocities into expressions to determine the height. So we did that by solving equations relating kinetic energy of each ball just after the collision to each ball's height after it swings up. And here these are two separate systems. One system is ball 1 in the earth. The other system is ball 2 in the earth. And so doing this, we get the expressions shown here for height 1 and height 2.
All right. Here we plugged in some numbers. We set L equal to 1.5 meters, theta equal to 80 degrees, mass 1 equal to 2 kilograms, and mass 2 equal to 3 kilograms. Our results are shown above, and we got a height for H1 is 0.05 meters, and H2 is 0.79 meters. As you can see here, all of our units are all calculations checked out, resulting in the expected values of meters or the length of our heights. All right, on to special cases. Our first special case, consider if the masses are equal, And as seen in the video here, I'm not sure if we can show it here, but in the video, he holds up these two balls and he lets go, and they bounce back equally to their original positions. Oh, sorry. Um, yeah, they essentially trade motion. The first ball stops upon collision, and the second continues with the exact velocity ball one had and moves up to its exact same height. As you can see, our work supports this outcome. Alright, our second special case considered if the mass of ball 2 was 0. In this case, the system should act as if there is no collision at all, or in other words, ball 1 should continue its motion unaffected and will rise back to its initial height on the other side. Our work here was again confirmed by showing h1 is equal to the initial height, L minus L cos theta. Our third special case considered if M2 approached infinity. It would be like throwing an extremely bouncy ball, like a racquetball, against the ground. In this case, the Earth's mass is just so proportionally bigger that we would see the smaller mass bounce backwards to its starting position with no effective change on the proportionally infinite mass. Our work again confirmed this result. Our third special case considered if M1 was greater than M2. Because of the ball 1's mass is bigger, it also has a higher kinetic energy, resulting in ball 2 to gain a large forwards momentum, effectively surpassing ball 1's initial height. Also, the momentum transfer causes ball 1 to lose momentum. Our math again confirmed this result. Overall, we see the ball's behavior depending on how their mass is compared to each other. This aligns in real life. For example, if two vehicles of similar masses collides, they would experience similar amounts of damage. On the other hand, if one mass was much larger, we could expect the smaller car to sustain more damage or bounce off more than a larger vehicle. Again, considering our final equations for the height, we can see that L minus L cos theta is in the numerator, meaning as L increases, the final height also increases. We can also see that as theta increases to 90 degrees, L cos theta approaches 0, making the initial height's maximum equal to the string length L. Finally, the longer this term is, the larger the height will be. So our expectations are confirmed. All right, Kobe.
Okay, so for reflection, we have many examples. So I will start with in the lecture. We discussed two balls moving toward each other that experience an elastic collision, and that from lecture notes 9.2. So also in another example in the lecture, from lecture is water slides exercise. So that help us with the ball one initially because it's same habit. So in the third one, I will talk about in the homework 9. The first activity featured a similar situation as the collision phase of this problem, but of course it's not exactly same. Uh, for the fourth one, I will say basically any problem from lecture or homework or studio that deals with the conservation of energy or conservation of momentum could be revisited as similar problem. Thank you.